Okay, this is example on page, this is the second example on page 156 of Hebden, and it's a titration question, but it also deals with percent purity. We're going to focus mainly on the titration part. If that's all you get from this question, that's fine, okay? If the percent purity part is confusing to you, then just be like, okay, it's the COVID quarantine, and this year I'm not going to get too excited if you don't understand that. So we'll do the core of the question and then we'll move on to the percent purity part, okay? So the core of the question is that we take a 3.4786 gram sample of impure NaHSO4 and we dilute it to 250 milliliters. And then we take a 25 milliliter sample of the solution, and that is titrated with 26.77 milliliters of 0.9974 molar NaOH. And what is the percent purity? Let us focus on finding the part of this question that is the regular titration part. We have a 25 milliliter sample of the solution is titrated with 26.77 milliliters of NaOH. Okay, and this is a sample of the NaHSO4 solution, and let's just focus on that part of the question to start. So in any titration, you need to make some conversions. Okay, so what I'd like you to do is in these 4 boxes, I would like you to write down what the steps for a titration question are. Okay, so take a moment and fill in those boxes, pause your video, and go for that. Okay, so we're going to be starting with our known substance, and we're going to be given some information about it. So we're going to start with the given info for our known substance. We are going to convert that into moles of our known substance. Okay, and from moles of our known substance, we're going to convert that into moles of the unknown. And from there, we're going to convert that into whatever we want to know about our unknown substance. Okay. Who is our known substance in this question? Pause the video and answer for yourself. Our known substance is the thing that we can actually calculate moles for, and that would be, because we have volume and molarity, we can calculate the moles of NaOH. So we're going to be starting with 26.77 milliliters of 0.09974 molar NaOH. Okay, we will convert that first into moles of NaOH. And then who is the unknown substance here? The unknown substance is the, we want to know, it says, what is the percent purity of the NaHSO4? So our next step will be to convert into moles of NaHSO4, and then finally we want the percent purity of the NaHSO4 SO4. And this last step is going to be quite complicated for this question. So that's step 1, that's step 2, and this is a very complicated step 3. But if you can only get through the first 2 steps of this problem, you are getting tons of part marks for this question if it comes up, and that is a fantastic thing. Okay, now before we go on, when we convert between moles of one substance and moles of another substance, which is always that middle step of any stoichiometry problem, of any titration problem, that step right there, step number 2, is always going to be using a particular conversion factor. What is the conversion factor to convert from moles of known to moles of unknown in a stoichiometry problem? Pause and answer for yourself. The conversion factor is going to be the mole ratio from the balanced equation. And what that means is that we must have a balanced equation. So we're going to need an equation that relates our NaOH and our NaHSO4. So let's see if we can come up with a balanced equation for that. NaOH plus NaHSO4. This could be fairly confusing, but if you focus on the fact that this is an acid and a base, and that when we have an acid and a base, what we're really focusing on is we're focusing on the reaction of the hydroxide and the hydrogen. And hydroxide and hydrogen always have to react in a 1-to-1 fashion. For every 1 hydrogen, you need 1 hydroxide. And if I look at this question, I say, oh my gosh, look, I have 1 hydrogen right now for every 1 hydroxide. So that's fantastic, okay? That 1 hydrogen and that 1 hydroxide are going to become H2O, okay? And then what are we left with after that? Well, we have an Na, and we have an Na, and we have an SO4. Well, look, that's Na plus, that's Na plus, that's SO4, 2 minus. Oh my gosh, my other product is going to be Na2 SO4. And am I really concerned about where all my spectator ions are going and things? Not really, because what I really wanted to know is that this is a 1-to-1 ratio, okay, between the NaOH and the NaHSO4. Had you wanted to, you could have written this as the net ionic equation, where you leave out the spectator ions because Na is a spectator for both of these. You could have written it like this: OH minus, which is what's left after we remove the Na, plus HSO4 minus, which is what's left after we remove the spectator, the Na, gives us, and remember the OH gets together with the H, giving us H2O plus SO4 2 minus. But it doesn't matter whether we write it this way or that way, because in either event we get a 1-to-1 ratio between the hydroxide, the sodium hydroxide, and the HSO4, the sodium bisulfate. All right. And that will give us our mole ratio. Okay, so this is going to be a 1-to-1 ratio up there. So let's go through and do the titration part of this question. Okay, so now we're going to do our actual math on this question. So we are starting with, and I'm going to do it actually in liters this time. I'm not going to use milliliters and millimoles because I'm going to want to do some other stuff with my moles here than just find the concentration. So maybe just having it in moles rather than millimoles will be nice. So let's start with 0.02677 milliliters of 0.09974 moles of NaOH per liter. Oh, and I wrote milliliters, but I didn't mean to because I've converted it into liters, so that's just liters there. Okay. All right, that would be step number 1 is done. Okay. Step number 2, we're going to convert moles of NaOH into moles of NaHSO4. So moles of NaOH into moles of NaHSO4. And that, we discovered, was a 1-to-1 ratio. Okay, and we're going to cut it off at that point. Do the calculation, 0.02677 times 0.09974 equals, and we get 2.670 times 10 to the negative 3 moles of NaHSO4. And if you feel like, hey man, titrations are hard enough, I've done the titration part of this question and I'm happy, you can just let that be at this point. If you might be going on to university to study chemistry, we're going to do the percent purity part because that is something you might be expected to do there, and it's nice to have at least had it introduced. I'm going to do this a little bit differently than in Hebden percent purity. In Hebden, they use the actual concentration over the expected concentration times 100. You can certainly do it that way. I might even show you that way at the very end. Instead of doing that, though, what I'm going to use is I'm going to use percent purity is equal to the actual mass over the impure mass. Okay, and when I say the actual mass, what that is that is the pure mass. So what's the percent purity? It's the amount of pure stuff in the total impure sample. Okay, and of course that would be times 100. So how are we going to use this? In our question, it says that we have this impure sample, which I'm just going to represent with a little box here, and it has an entire mass of 3.4786 grams, and that's of the impure NaHSO4. And what that means is that in that 3 point whatever grams, some of it is sodium bisulfate and some of it is other stuff. So we have a percentage which is other stuff, and we have a percentage which is sodium bisulfate. Okay? Now, if we can find the mass of pure NaHSO4, which would be this part, like that, okay? If we can find the mass of the pure NaHSO4, then we can divide it by the mass of the impure NaHSO4, and we can find our percent purity. So where are we starting from to find this mass of the pure NaHSO4? Well, we know that we calculated that there were 2.670 times 10 to the minus 3 moles of NaHSO4. So we had 2.670 times 10 to the negative 3 moles of NaHSO4, and that was in a 25 milliliter sample. Okay, because what we did is we actually took our impure sample, and we dissolved it into 250 milliliters of solution. Okay, so we have 250 milliliters of solution. And there's some of the red stuff in there, the other stuff. Okay, so there's little other stuff in there. But there is also, okay, the NaHSO4, which I'm going to represent by little black stuff. Okay, and there's a lot more of that. Okay, the red stuff just won't react. And in here we have, we don't know how many grams of NaHSO4. All we know is that it's going to be less than 3.4786 grams. Okay. So we have this in our 250 milliliters, and then the question says that we took a 25 milliliter sample of this. So we did not use this entire volume. We took 25 milliliters of this. And the 25 milliliters contained 2.670 times 10 to the minus 3 moles. Well, how many moles then would that make in our 250 milliliter sample? How many moles in the 250 milliliters? And that's moles of NaHSO4. Well, our math is really easy in this one because in order to get from 25 to 25 to 250, you have to multiply by 10. Okay? So if we had 2.670 times 10 to the minus 3 moles in 25 milliliters, if we have 10 times the volume, we will also have to have 10 times the moles, and so that will end up being 2.670 times 10 to the negative 2 moles of NaHSO4 in the 250 milliliters. Okay? So we could figure out how many grams, because we want, this is the total moles of pure NaHSO4, right? Because our 250 milliliters contained the entire dissolved sample, the entire NaHSO4 and other stuff, but really we're just concerned about the black part because it's the only part reacting. Okay, and so we would like to find then grams of pure NaHSO4. And we get, well, we have 2.670 times 10 to the negative 2 moles, excuse me, of NaHSO4. And we want to cancel moles of NaHSO4. And we want to find grams of NaHSO4. And for that, we need the molar mass. Thank goodness Hebden calculated it for me. It's 120.1 grams per 1 mole. Okay, we do our multiplication there, and we get 3.2067 grams. of the NaHSO4. So that's how much we actually had. That's how much we had here, okay, back in our original sample. So we actually had 3.2067 grams. That's the black portion, which is the NaHSO4. So what is our percent purity? We're going to take that many grams, which looks like a good number of grams, doesn't it? You know, 3.2 out of 3.4, that looks like a good percentage. It looks reasonable. I actually had done this before. You're getting my second version of this. And I got 32.067. And I was like, that can't possibly be right. I had forgotten a zero somewhere, okay? So I think instead of 0.099, I'd use 0.99, okay? So check your answer and see if it's something reasonable. Now we're going to do our percent, okay? Our percent purity, which is equal to the, well, not the impure mass, the pure mass of the sodium bisulfate over the impure mass. Okay, and that's times 100, and we have 3.2067 grams divided by 3.4786 grams. And then we're going to multiply that whole thing by 100 divided by 3.4786 equals, and we get 92.18%.